a little bit further to begin with. If I happen to give you an initial electric dipole that was not oriented, let's say, up to the right here, but down to the right, so it was pointing down here, what direction would it tend to want to turn if it was starting off in that orientation? So it's again going to want to go so that the dipole is oriented parallel to the E field. Okay, now a little bit of high-level thinking from first semester. If I do start off in this orientation, and there's a torque exerted on this thing, what does that tell you about the angular acceleration of this electric dipole? Just a reminder from first semester. So tell me about the acceleration of this dipole as it starts rotating.
It's non-zero.
Okay, so it's accelerating with a variable acceleration. Actually, the acceleration is decreasing as it comes down here, if you think about it. But it has angular velocity at this point because it's been accelerated. So it's rotating. It's approaching being parallel to this, but now it has some angular velocity. So what happens? Jesse? Come on, that was pretty good. I've got a lot of good miming going on this morning. Let's hear it.
Well, it has to like oscillate slow. Like it's like a seesaw.
Okay.
It's like
Indeed, it is like a seesaw, right? Because it has angular velocity here, and so it's going to overshoot. And so it's going to overshoot. Once it overshoots, there's a torque that's tending to rotate it back. Angular velocity, it overshoots. So indeed, it's going to oscillate back and forth. Now, is there necessarily any energy dissipation in this system as you've described? It's not a trick question, really. Right, there's nothing that really would dissipate energy. We're not talking about mechanical bearings here, there's no friction, anything like this. So in fact, if I started this thing off like this and let it go, it's going to oscillate back and forth, going equally far in terms of angle on this side before it turns back. It's going to oscillate back and forth indefinitely. If there's some energy absorbing mechanism, that's not true. It's going to be damaged. So now it's oscillating back and forwards. So there's a fair amount of interesting stuff going on. So let's try and move on with this because I do want to start talking about Gauss's law. So now you've got the setup, you've got a sort of conceptual and qualitative understanding of what's going on. Let's make it a bit more quantitative. So first off, the net force is always zero. The net torque may or may not be zero, but it is zero for P parallel to E. Is there one other orientation where there's no net torque on this electric dipole? So I'm talking about the case where P and E are parallel. Is there another orientation where there's no net torque on this thing?
Is it when it's anti-parallel?
Yep. Or, and I don't know how I'm supposed to write this, but that's going to be anti-parallel. Okay. Elizabeth.
Well, the diagram, the positive charge will move toward the negative charge. So it'll attempt to get to parallel where the positive is negative.
So positive, negative, you mean?
Like if it's turning that way, would it need to be the negative plate on that?
Yes, and that's embedded in the fact that the electric
Oh,
field
yes.
is left and right. Yes.
And it wouldn't turn the other way. Like you're saying anti-parallel, parallel, but it wouldn't.
So it wouldn't want to on its own volition, but maybe I would put it there. So yeah, I could make it anti-parallel, and indeed there's no net torque in that case. So it's stable. You'll remember when we talked about potential energies and gravity in first semester, I showed you a demonstration, for those of you in 1601, of stable and unstable equilibriums with objects on the top of spherically concave or convex surfaces. We've sort of got a slightly analogous situation here. I have two equilibrium orientations, parallel and anti-parallel. One of them is stable, one of them is unstable. You remember how I defined that. stable equilibrium means if I perturb it from an equilibrium point, it's going to tend to go back to that equilibrium point, which means parallel orientations here are stable equilibrium. By contrast, if I have the anti-parallel case and I perturb it slightly from being anti-parallel, then the thing flips around. So that's an unstable equilibrium, okay? So some kind of just things to be aware of. All right, so now we know this. Let's go back and remind ourselves what torque is. From first semester mechanics, this is going to be slightly annoying because this is momentum and this is electric dipole moment. Even worse because they both begin with MON somewhere in there, but this is momentum, linear momentum, this is electric dipole moment. Okay, whoops, sorry, that's not good. Definitely won't help you scratch anything about momentum. Okay, R cross F. So, R cross force. So we can figure out just from the geometry what this looks like. And it looks like twice, because there are two forces, one from here and one from here, twice F d over 2 sine theta. Again, throw back to first semester, a bit of geometry here, we're calculating torques, moment arms, this sort of thing. Force, moment arm is d over 2, that's the distance from the center to one of the charges, and then we have to fold in the sine theta to get the perpendicular distance from moment arm. So we get this, and it tells us now that this is f d sine theta, or we'll make this a magnitude, and so this is QE. So now, take a quick look at what I'm doing here. I've got QE times D times sine theta. I'm going to fold this in, and I'm going to combine Q and D to make the electric dipole moment P times E times sine theta. And so, I can, doing this, say that the actual torque on a dipole in an external electric field is that. Okay, so having confused you inappropriately with P's, now you see P appear back in the torque equation, but now as an electric dipole moment. So we get from our original mechanical torque definition, look at the geometry, plug in our definition of electric field here, throw in our electric dipole moment, and we end up with this. Okay? So this is a slightly useful, more than slightly useful, now expression that we're going to use to figure out the magnitude of a torque on an electric dipole in an external uniform electric field. Okay, so probably okay. Let me just ask you if there are any questions on that. Yeah, no.
So about the equilibrium, so is the first equilibrium that's with like attractive forces, and the second equilibrium with like repulsive forces? Because it's like the orientation of the like plus and minus Q's on the dipole, right? With respect to
I don't want to generalize it in quite that way because that's not quite a true overall generalization. I mean, in this case, yes.
Okay.
Because just by nature of the fact that the external electric field tells us which direction these forces act, and indeed in the sense that positives are attracted to negatives, and vice versa, then it all is self-consistent. But I don't want to follow what you said as a more general principle because it isn't. But in this case, what you said is true. Yeah. Okay, so we have to worry, as we did in the first semester, with directions of things here. You'll recall in our convention for Newtonian mechanics when we had torques going counterclockwise with respect to some defined axis, we defined them as positive. And if they're going clockwise with respect to that defined axis, we define them as negative. Right? And we also had our cross product and right-hand rule embedded into all of that. In principle, all of that holds. And in this sense, if I was to follow that sign convention, this would actually be, again, if I was following that sign convention, it would be negative because it's tending to turn this counterclockwise with respect, let's say, to the electric field. Okay, so just be aware of the sign aspect in general. I don't care about it, but it's just something to be aware of. All right. I was unsure about whether to do this now, but it appears at this point in Sears, which is a little bit out of place. We are talking about a conservative force. So, way back over here. Conservative force, remember from first semester in the context of gravitation, gravitational fields, and you're starting to see more and more parallels between electrostatics and gravitation. We're talking about conservative forces. If we have conservative forces, what is the kind of next concept that you're likely to invoke in the case of conservative forces? Way at the back. That wasn't what I was looking for. Simple harmonic motion I associate with a number of things, but in particular in this cases where we've seen things so far in terms of linear restoring forces. But what about the more generic case of conservative forces?
Energy.
Okay, and what type of energy? Potential energy. So, this is conservative. And many of the things we talked about in terms of associating conservative forces, of course, they're all going to carry over. Doesn't matter how I go from A to B. The amount of work done is independent of path. That's one way of describing a conservative force. And then associated with that is the idea that we can define a potential energy. So, again, a bit of an aside here. We can assign a potential energy with this little electric dipole in an external E field. I'm going to be fairly brief on this, not because it's unimportant, but because it will make a bit more sense in a week or two when we really come back and talk about potential energy in the context of electric forces. But let me just give you the outline, and I'll try and make it in a way that is at least plausible. So potential energy of a dipole in an external E field. Well, that's our guiding consideration. Change in potential energy, as always, is defined as a negative of the work done by a conservative force. So the conservative force, in this case, is the Coulomb force. And the work done, well, we're talking about rotations here. So work done as I change the orientation of this dipole. Again, throw back to first semester. Work done by a force or a torque. Anyone recall a rotation-specific expression for work done by a force that's causing a rotation? So let me just give you the sort of first ingredient to this. There's our definition of work to begin with. And then how does this carry over? Bless you, kind of. How does this carry over into an angular scenario? Joseph?
That work is equal to the integral of torque, function of torque times E theta.
Okay, excellent. So this is linear. This is rotation. So this is our carrying or driving expression in this case. So I can, in this case, fold in this. And again, I'm not going to quite go through all of this, just because it's a little bit jumping ahead. But it turns out that I can write this as minus PE cosine theta. So this is just a preview. And I'm not going to bug you about it for a little while yet. But I just want you to understand where it is. Usual definition of potential energy, change thereof, work in a rotational context. We know the magnitude of the torque over here. And so it turns out that this is the result. And in a more crisp notation, I can embed the cosine theta here by making it part of a scalar product. And I can write this as the change in potential energy of this dipole as it rotates is simply minus P dot E. Okay? So again, I'm not going to go over this too much in class. We'll come back to it in a couple of minutes where we fully define potential energy in an electrostatic context. But what I want you to take away from this is how we get there. You know the ingredients. What does it mean? It means, of course, that the energy associated with this varies with angle. And if you look at this and maybe think about a little bit your comment, Noah, about where this thing wants to be in terms of forces being attractive or repulsive and stable versus unstable equilibriums, where does it have the lowest energy and where does it have the highest energy in terms of orientations here? So where is its stable point, which if you think about it corresponds to the lowest potential energy, think of gravitation. Where is its unstable point, or its most unstable point? Let me go to the back.
It's not stable when it's the dipole is perpendicular to the electric field.
Careful. That might be a reasonable conclusion by looking at the math and the behavior of the scalar product, in the sense that you would get zero in that orientation. But is zero necessarily the smallest value of this quantity? You want to give it another go? Well, either of you?
Well, I mean, it needs to be,
A little louder?
I believe like the most stable configuration, the one where it's one
I didn't catch the end.
where it's oriented parallel.
Right. So it's most stable when P and E are parallel. And that turns out to be the lowest value of the associated potential energy with this definition. So this is, of course, negative in that orientation because the scalar product is 1. But negative PE is still less than 0, which is itself less than positive PE. So the lowest energy configuration is parallel. The highest energy configuration is anti-parallel. And we happen to set the 0 point with this definition as being perpendicular to your point. So it's a question of allowing us to set the 0 point wherever we wish, for convenience, and mostly being worried about the change in potential energy. So again, hopefully we'll have time to come back and review this in a little bit more detail when we fully introduce potential energy in the context of Coulomb forces. Okay, I'm going to leave it there and turn our attention to Gauss's law just to keep things moving. So, step back. What's our big picture goal here? Electric field calculations still, but maybe now from more complicated continuous charge distributions. So I'm going to call this electric fields from three-dimensional charge distributions. And as we talked about in the intro comments, this would start getting mathematically a little bit tricky. As you guys learn more calculus and more techniques for doing integration, you will have more knowledge to solve really three-dimensional integrations, but for now, we're going to kind of set that aside and see if there's a better way of doing this, or at least a different way of doing it. Okay, let me introduce some concepts. I'm going to define a point-like positive charge sitting in space like this. What does the electric field look like around that point-like positive charge? Nice. Radial lines heading outwards. Now what I'm going to do is imagine a surface, spherical surface, centered on the positive charge of some certain radius. Maybe it's got a radius big R or maybe little r, doesn't matter. So let me just write this, maybe a little r. So it's a spherical surface centered on the charge. Okay, what is the electric field anywhere on that surface to the distance little r away? The electric field in magnitude is, let's see, K, I didn't define this, but I need to. Electric field KQ over R. Here we go. So, there's our electric field anywhere on that spherical surface. What's the surface area of that spherical surface? This is R squared. Yep. What's the surface area of the spherical surface? Let's go way to the back again.
4 pi times r squared.
Okay. Area is 4 pi R squared. Okay, let me, for no good reason, take E and A and multiply them by each other. Okay, what do I get? Huh? Okay, don't get fancy yet. What do I get here? Huh? What in terms of algebraic symbols do I get here? U over epsilon naught. So you've kind of, well, I'm good because you guys have been reading ahead, because you have to. You've invoked the idea of flux, and you've actually arrived at a divergence theorem / Gauss's law. So, what is it? It's obviously a very special case. Fine, we can obviously make it general and make it useful. So we've defined the electric flux, kind of. It's this. And it is in fact a product, and it's going to turn out to be a special product, of the electric field, a vector quantity, multiplied in a certain way, which we have to elaborate on, by the area of some enclosing surface. So this is kind of the electric flux, so it's not quite sophisticated enough to be called that yet. In this particular special case, it turns out it's exactly this. So again, invoking the idea of divergence theorem and Gauss's law, this is the net enclosed charge. Sounds unnecessarily complicated for now, but that's going to turn out to be what it is. It's certainly the enclosed charge. And it turns out they're related to each other, and they're related simply by some constant, happens to be 1 over epsilon. Joseph. So remember here, this is 1 over 4 pi epsilon naught. That's kind of our shorthand for that. So 4 pi's cancel, the r squared is cancel, and I'm just left with q over epsilon 0. Yep. All right, so what it's telling us in this simplest possible case is that this thing called the electric flux is proportional to the enclosed charge. Again, divergence theorem, this is in fact Gauss's law in words. We just have to be a little bit more technical about how we define the electric flux. So divergence theorem in math relates how much of some vector, usually vector always, quantity passes through some surface in a certain particular way, and it relates that to what's enclosed within that surface. Okay? And in this case, it's very much associated with electric field and electric charge. That's what Gauss's law is all about. Okay, so if you look at this, I set this up with a very precise and very simple geometry in the sense that the electric field is always penetrating this surface perpendicularly. So everywhere here I've got a surface element, the electric field is passing through it perpendicularly. We need to explore that in a little bit more detail. see if we can better define this idea of electric flux. So let me do that. I'm going to take a little piece of surface, and for now it doesn't necessarily have to be a totally closed surface, just a piece of surface. So electric flux defined. Okay, a little bit of surface here. So we're going to do a bit of just some wavy piece of surface. I'm going to break it up into small area elements. Whatever these look like doesn't matter, but here's a small area element dA here. So this is an area, some random area. It's a wavy plane. There's a little bit of surface area dA here. And I'm going to do something slightly weird the first time we do it, which is I want to define a single vector to unambiguously tell me what direction that area element dA, what plane it sits in. Okay? If I make this small enough, it's flat. Okay? How can I use a single vector? And we talked about this when we introduced this with rotations and torques in first semester. How can I unambiguously assign a vector with a plane in such a way that it unambiguously defines the plane direction?
Take cross traffic vectors.
Make it simpler for me. All I want to do is pin a single vector on a plane to tell me what direction the plane is in. So behind you.
Vector perpendicular.
Yeah. Okay. So I'm not going to be able to draw this in a particularly smart way, but this is supposed to be perpendicular to that little area of plane. Think about it. I have to make it perpendicular. If I do, I unambiguously, once I know how I define it, know that the plane is perpendicular to it. That's the only way I can use a single vector to define a flat element of surface. If I try and put it in the plane, it's not unambiguous. Think about it. So we always do this. We always define the area vector as actually being perpendicular to the plane anywhere. Now, in terms of flux, what I care about is the orientation of the area locally with the electric field that somehow is passing through it. Now, this may or may not be uniform, but again, what I care about is the relative orientation of the electric field as it passes through this tiny little surface area element. Now, if you think about it, there's a sort of analogy here with flux that I often use. It's okay, it's not perfect, but it's the idea of something flowing. A fluid is the most obvious thing to think about. But the red thing is the flow of some fluid. It's a vector quantity, something that's flowing. Now, we don't traditionally think of electric field as something that's flowing per se, but imagine like water flowing through a mesh net or something like this. The relative orientation of the water flow locally and the little squares in the mesh net is important. If I have water flowing exactly parallel to the surface area or the mesh net, then there's no water flowing through the net, it's just flowing parallel to it. In this sense, if I have the electric field parallel to the area locally, there's no electric field passing through that area element. So if I'm thinking about flow of something, the relative angle of the E field, in this case, the vector quantity, and the local area element is obviously important. What we actually care about is the component of that vector quantity that is perpendicular to the local area element, or, in other words, it is parallel to the local area vector. Okay? So, the wording is very important there. The contribution to this thing that we call flux usually goes with the symbol big phi. And even though I doubt our textbook does this yet, I'm going to start doing it right away. Put a little e here to denote electric flux. The reason for that is in a few weeks we're going to talk about magnetism in a similar way, and we'll define a magnetic flux. So again, I doubt our textbook does this, but electric flux. it is the local electric field scalar product with the local area vector. So the electric field is whatever it is here, it's given for us. This small little area element, the area vector is perpendicular to it. And the scalar product gives us this directional projection, if you will, of the electric field into the part that's going through that area